First thing we're going to do today is just recall tangent of theta, refresh our memories, and do one more practice question. So whenever you're graphing tangent, if it's a year from now or 2 years from now and you can't remember the graph of tangent, what you want to do is lay out your axes and put the tick marks of the quadrantal angles, all right? You may need to, on the side in your brain, think a little bit and think to yourself, well, what is tangent equal to? Tangent is really what over what? Sine theta over cosine theta. So you may need to think, what ratio is it so I remember where it's undefined. So that's your thought bubbles, okay? You're thinking. Now, from there, where does tangent equal 0? Do you guys remember?
Pi over 2 and 3 pi over 2.
No, tangent equals 0 at? 0 and pi and 2 pi. Right there. Where is tangent undefined? Good, so we'll have asymptotes right there because that's how we indicate where a function's undefined on its graph. It's an infinite discontinuity. All right, so we have our asymptotes. Now, these quadrantal angles are also breaking our theta axis into the quadrants. So the space between 0 and pi over 2 is really representative of quadrant 1. Now, in quadrant 1, also keeping in mind, these little red tick marks are all going to be my 45-degree angles or my pi over 4 angles. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. You might want to check in there. But what is the tangent of pi over 4? 1. What is the tangent of 3 pi over 4? Tangent of 5 pi over 4?
1.
And tangent of 7 pi over 4? Boom. So now we can draw in those little branches. So my graph will look something like this right over here. We're going to start at the 0, pass through that point. I'm going to draw that guy right there. Got a little concavity. The inflection changes at the x-axis. How many complete periods did we just draw? 2. What is the period equation for tangent?
Pi over b.
Period is pi over b, right. It's not 2 pi over b like it was for sine and for cosine. So we have period is pi over b. And how much of the period do you really need to find? Half of it, okay? So we're going to find half of the period. Now, if you found a quarter of it, that just means we would actually have the red tick marks labeled. That's all. We don't need to do that for our graph. That's not that important, but if you want to, you can, if you still wanted to find a quarter of it. Okay, so that's the parent function for tangent. You need to remember what it looks like. Cotangent is similar. It has similar qualities, but it's different enough that it really confuses people, okay? So next example we have here is a completely transformed tangent function. How does the 2 affect our tangent function? What does it do? Stretch which way? Vertically, good. What about the +1? How does that affect our graph? Moves it up 1. How about the minus pi over 5? To the right. And lastly, the 3/4. How does that affect our graph? Horizontal stretch. Because when you divide by 3/4, you're really multiplying by what? 4/3. And multiplying by a number greater than 1 makes something bigger. So it is going to stretch it out. Now, my axes are already drawn for me. Since it's to the right, I drew my y-axis all the way to the left. But we talked about the other day, when you shift your graph to the left, don't draw your y-axis until you've already labeled your entire theta axis. All right, so where do we want to start? Give me something to do. Find the period? All right, we can do that on the side. So the period formula was pi over b. And I'm going to write the formula first. Good habits, all right? Pi over b. And then I'll have pi over, which equals? Good. So there's our entire period. We find that so we could figure out our half period, which is going to be 4 pi over 6 or 2 pi over 3. So we may need to change it back to something over 6, but we'll see later. All right, so we have 2 pi over 3 as the half period. Now, after I find the period, what else can I do?
We'll have to, like, plot the x's.
Plot the x's, all right, or the thetas. That's fine. So I'm going to do 5 tick marks. 1, 2, 3, 4, and 5. First one will be what?
Pi over 5.
Good. A lot of people accidentally put the period there or something, so just be careful. Now, here's the dilemma. Pi over 5, I have to add 2 pi over 3, and that doesn't match. So how can I rewrite pi over 5?
5 pi over 15.
How much?
10 pi over 15.
10 pi over 15.
Right there.
Guys.
3 pi.
There we go, honors kids, come on. 3 pi over 15, sillies. Now we're gonna add 2 pi over 3, but 2 pi over 3 is actually,
10 pi.
that's the 10 pi over 15, thank you. So we're gonna add 10 pi over 15 each step of the way. So what's my next tick mark on here?
13 pi over 15.
Yep, and we're just gonna keep really adding 10, so 23, 33, and so on. All right. Oops. All labeled. What can we do next? Draw in the what? The sinusoidal. Okay, good. Where do I draw the sinusoidal axis?
At 1.
At what equals 1?
Y.
Y equals 1. So we're going to draw in at y equals 1, the sinusoidal axis. I'll make mine green. So right over here at 1, I'm using each line basically as a unit. Okay, that's done. What else can I do?
Make the other points.
Make the other points. All right.
Connect the other points like on the y axis.
Okay, what points would those be that I'm looking for?
3, negative.
Good. So here is 3, and down here is -1. All right. Those are going to come in handy. Now, you may not see why they come in handy, but I'm going to do a little red on here. This point and this point will come in handy for these guys. But we'll get to that. All right, what else? Asymptotes and the zeros. So does tangent, when you're going around the unit circle, start at the first place. Is tangent 0 there, or is it an asymptote there?
0.
It's 0, right. So that means over here, I'm going to plot a 0 first. That's like my 0 radians. Next, I'm at my pi over 2, which became 13 pi over 15. What does tangent equal there?
Undefined.
It's undefined. So we're going to have a vertical asymptote right there. Then at 23 pi over 15, that's basically like my pi. I'm 0 again. Next, 33 pi over 15, that's like 3 pi over 2. So that's another vertical asymptote. And last, 43 pi over 15, that's my full time around the circle. That's like my 2 pi transformed. So it's a 0 again. All right. What other points can I plot?
The exact points.
The in-between ones, the 45s or the pi over 4s. All right, we don't need to know what their values are right now. They don't represent a point of inflection or a max or a min. They're just there to help us stretch out our graphs. So I don't really care about their theta value right now. But I do know that I'm going to have a point right there at this little spot. Do we all agree? Okay. And I'm also going to have a point down here at this spot. Oops, sorry. And we'll have one more here. And one more down there. So I can draw in my branches, something like that. And there's our lovely tangent graph. Amazing. Now the last thing we need to do is find our domain and range. So what is the domain going to be of this tangent function?
All real numbers such that
All real numbers, such that. Go ahead.
theta doesn't equal
Theta doesn't equal
13 pi
13 pi over
over 15,
15, yes.
plus
Yep, plus.
20 pi over 15.
Let's get to the next one. 20 pi over 15. N, where n exists in the set of integers. Beautiful. Now we could also find the range. This one's even easier. All real numbers. Goes up and down forever. Got it? Geniuses? I feel like it looks way more impressive and it looks way more challenging than it actually is once you know the unit circle. Okay? All right, we are going to have another example now. What we have is this cosecant graph. Now, yesterday we had talked about cosecant, and you guys were actually really good at figuring out what the graph of cosecant looked like, right? Now, just for a second on the side, and we're going to erase it when we're done, but all I'm going to do is I'm going to do a little sketch. Over here, I have a sine wave, okay? My sine wave looks something like that. Cosecant is the reciprocal of that sine wave, right? So everywhere that sine equaled 0, what will cosecant be? Undefined, so they'll put an asymptote there, right? Everywhere, though, that, say, sine equaled 1, what does cosecant equal?
Oh, no.
1. It's the same thing. Good. Trick question. What about when it equals -1? Same thing. However, where sine equaled 1/2, what does cosecant equal? It equals 2, so it's up there. Where sine equaled 1/3, what does cosecant equal? 3, so it's up even higher. So that's why the branches do that and that. Okay? So cosecant's that little graph in red. So all we need to do is graph the sine wave. I'll draw it dotted, so it's not really there, dashed. And then we will use it as a skeleton to finish off the graph of cosecant, okay? So I'm going to pause the video right now so you guys could get a little head start, and then we'll check in with each other in a second, all right? So get your attempts going. All right, so we have a lot sketched out already. The first thing that we did was on top there, we had to factor out that 4/5 in front of theta. If you don't factor that 4/5 in front of the theta out and you use 2 pi over 7 as your horizontal shift, you're going to get the wrong graph, I promise. So we want to factor that out. Now, most of you are probably used to factoring out a GCF like 2 from a bunch of even numbers where life is easy. But in this case, we have to factor out a fraction, and we're actually factoring out that rational expression from another rational expression that has pi in it. So earlier, we talked about techniques for factoring that out and how you should be thinking of it. So I'm just going to repeat that. I'll erase this in a second. But you want to think of those parentheses on their own over here on the side. So 4/5 theta minus 2 pi over 7. Now I want to get a 1 in front of that theta. That's what we want. So I'm going to multiply on the outside by 4/5 to get it out front, kind of like the whole idea of factoring it out. But to keep things balanced, you could divide everyone inside by 4/5, which is kind of odd to do when you have all these fractions. Or we could multiply by what other number? 5 over 4. So in the end, that 4/5 will be out front like it is right over here, right? And then the 5/4, when it distributes, you'll get just a theta. And then we'll have 10 pi over 28, which reduces to 5 pi over 14. All right? So we should all get that. And if you need more practice with that, you can make up your own examples, just fractions, distribute them, and then try factoring it back out and getting what you started with, okay? Now that it's all in that nice form for us, we can get our graph going. I found the period first, 2 pi over b, flipped and multiplied. I got 5 pi over 12. Found a quarter period next. We find quarter periods for sine, cosine, cosecant, and secant. And we got 5 pi over 8. But I needed to add 5 pi over 8 to 5 pi over 14. They have a common numerator, but they don't have a common denominator. So unfortunately, our common denominator was 56. We changed 5 pi over 14 into 20 pi over 56, and then added 35 pi over 56 until we got 5 tick marks on our paper. From there, I drew in the sinusoidal axis at 2. Did the rest of you guys do that?
Yeah.
Okay. Then I more or less sketched the sine wave. All right. I pretended it was sine and I sketched that using a dashed line over here in purple. Then everywhere sine equaled 0, cosecant equaled undefined, which indicated an asymptote. All of our maximums and minimums are sort of marked out for us. So what's the last thing we need to do? Draw in those branches, right? Those little U-shaped guys. So we got one right there and one right there. Did everyone get that graph? All right, good. Now, last thing we could really write down. Let's do our domain and range. What do we get for our domain? Someone I haven't heard from, maybe? Go ahead, Katie.
All the numbers such that beta is not equal to 20 pi over 56 plus 70 pi over 56 and 70.
70, sorry. I'm zoomed in on my end, so I can't see. 70 pi over 56 and comma nes and exists in the set of integers. And 70, that's the space. Yes. Okay, good. Looks great. And last, the range. What's the range for this one?
Negative 1 with the
-1 with the bracket.
bracket.
Good. Inclusive.
Union 5 to infinity.
Oops, ran out of room, so we'll do it down here. 5 to infinity. Beautiful. Got it?
Yeah.
All right. So now what we're going to do is we are going to discover, the way we did yesterday, the graph of secant. So who do you think you need to graph in order to graph secant? Cosine. Now, we could do it the way we did the other ones. I want you to go from -2 pi to 2 pi. Okay? Picking up what I'm putting down? So we're going to do more than one complete period. It'll have 2 complete periods, but that's okay. So you're going to include all those tick marks. So I'm going to pause the video, and you guys could check in with each other and see if you guys have the same graph in a few minutes, okay? Pausing. Basically, what we need to do for secant is set it up the same way we set up cosine, but I'm going to draw my cosine wave, but I'm going to draw it in dashed because, again, it's the skeleton, and it's not really there. So I have these points, and you should have your waves, your mom waves. Oops, I didn't draw them dashed. But draw those in dotted or dashed, whatever word you want to use. From there, everywhere cosine equals 0, what does secant equal? Undefined. So we draw in vertical asymptotes. So here in this picture, we're going to have 4 vertical asymptotes. Everywhere we had those maximum points, they're basically going to flip and become a low, a minimum point. And you're going to have those little U shapes again. So final picture will look like this. And it's a little weird, but you only have half of one at the end over there. So that's secant. So I will post a homework example for you guys, but good job today.